What you're listening to here is a sequence of pitches based on the Fibonacci numbers, specifically the Fibonacci numbers modulo 12. It gives rise to this really interesting repeated pattern, and the more I looked into it, the deeper and more interesting it became, which is really interesting because it's such a short and simple script. So let's dive in. So to start with, let's not worry about the modulo 12 part. Let's just make a sequence of pitches based on the Fibonacci numbers. So we're going to start by importing everything from the scamp libraries, creating a new session, setting the tempo to 120, creating a new clarinet part, and storing it in the variable clarinet. And then to get a sequence of Fibonacci numbers, all you have to do is start with A and B equal to 1, right? And then while true, we're going to play a note based on that. And then we're going to have A equal B and B equal A plus B. It's really nice in Python. You can do this in a single statement without having to create a temporary variable. So if I were to comment out the playing of the note and just print A each time, and then maybe wait a fifth of a second so that it doesn't just explode, you can see we'll be printing out the Fibonacci numbers below here. There they go. Okay. So to turn this into a stream of notes, all I'm going to do is start with pitch 64 and just add whatever the Fibonacci number we're on to that pitch. Volume of 0.7, duration of 0.25. Let's take a listen to that. And there's the problem with Fibonacci numbers. Fibonacci numbers get big very quickly. So if we want to do something interesting with them, we have to somehow kind of keep them within a range of reasonable notes. And a natural, easy way of doing that is to use the modulo operation. So for those of you who don't know, modulo is basically just the remainder when you divide by a certain number. So if I were to write down here 12 modulo 5, it's the remainder when 12 is divided by 5. So that's 2. So the great thing about using a modulo in this case is if I did like some gigantic number, modulo 5, the result is still going to be either 0, 1, 2, 3, or 4. This is good with the Fibonacci numbers because, as I said, they get gigantic pretty quickly. So the only difference I'm going to make to my code here is instead of setting B to A plus B, I'm going to set it to A plus B modulo 12. I'm going to go ahead and also print the Fibonacci number that we're on each time so that you can kind of see them as we go. Let's take a listen. So the first thing that you might notice is that this creates a cycle, and it absolutely has to create a cycle because there's a finite number of possibilities. To show you, let me look at the Fibonacci numbers modulo 3. So I'm going to change this to a 3 right here, and I'm also going to say end equals comma here so that they print out on the same line. Let's take a listen. So you can see here, 1 plus 1 is 2. 1 plus 2 is 3, which has a remainder of 0 when divided by 3, so it's a 0. 2 plus 0 is 2. 0 plus 2 is 2. 2 plus 2 is 4, which has a remainder of 1 when you divide by 3. Then 2 plus 1 is 0. 1 plus 0 is 1. 0 plus 1 is 1. And then 1 plus 1 is 2. That's where the cycle repeats. Because from then on, it's going to do the exact same thing that it did before. Now you know that this has to happen eventually because of the pigeonhole principle. The truth is that there's only 9 possibilities for what A and B can be, right? You know, A can be 0, 1, or 2, and B can be 0, 1, or 2. So if we select any pair of numbers here, it's going to be one of 9 possibilities. 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. The longest possible cycle we could get is if we get a distinct pair each time. So in this case, the longest possible cycle would be 9. Interestingly, that's almost what we get. We have a cycle of 8. Can you spot the pair that isn't in the cycle? It's 0, 0. Because if we had 0, 0, then 0 plus 0 would be 0, and 0 plus 0 would be 0, 0, 0, 0, 0. It would just be an infinite string of zeros. So that's the pair of numbers that we never run into, and we run into every other possible pair of numbers here. Let's try some of the other moduluses. So let's try, how about 6? There's repeating. How about 13? That one's kind of fun. How about 14? There we go, we finally let it repeat. That was a long one. And well, let's try 24. I noticed that one was kind of interesting. So 24 is kind of interesting because it's not that long of a period, right? It's actually a period of 24. But if you think about it, there's a lot more possible two-number pairs than just 24. I mean, there's actually 24 times 24, which if we go down here, 24 times 24, there's 576 possible ones. So we could have a cycle of 576, but instead we have a cycle of 24. Okay, so this got interesting enough for me that I was thinking someone else has definitely thought about this. And I looked it up, Fibonacci numbers, modulo, whatever. And I came across this, the Paisano period. And what the Paisano period is it's literally the length of the sequence of Fibonacci numbers taken modulo n. And you can see there's a chart down here where we can see the Paisano period of different numbers. It's structured in terms of rows of 12 for some reason that I would probably understand if I read the whole Wikipedia article. And you can see that 12 plus 12 right here, this is the cycle of 24, and it's saying the length is 24. But it's a little bit irregular. You can see here the modulo 10 has a cycle of 60. Let's try it out. So change this to 10. There, it finally repeated. So for some reason, modulo 10, you end up with a much longer cycle. Remember, the longest possible cycle you could get with 10 is 10 times 10, which is 100. And of course, you're never gonna get 100 because the 0-0 pair is always gonna be just a string of zeros. Let's look for one that has a really long period. So 48 plus 2. So 50 apparently has a period of 300. Let's check it out. So because it's gonna be 50, I'm gonna make the notes a little bit lower. I'll set this at 55. And I'll set it modulo 50. Let's take a listen. Still no repeats, right? That was pretty interesting. It's almost in reverse. There we go. There's the repeat finally. Actually, the spot where it was almost going in reverse is pretty fascinating because look, that's right here, 49, 49, 48. That's actually 49 is -1, right? It's -1 modulo 50. So it's probably literally doing the entire sequence in reverse. Come to think of it, I think I read something about that in the Wikipedia article. Anyway, go read the Wikipedia article. So one last thing that I think is really interesting, let's try the cycle of 29, which I happen to know is a very short cycle. It's only of length 14. Let's take a listen to that. So because this is such a short cycle, there's a lot of pairs of numbers here which are not being used. So what if we tried starting with one of those pairs of numbers, like A and B? Let's have them both start as 8. There's no 8, 8 in the sequence. So that should give us a whole different cycle. Let's take a listen. Or maybe 8, 7. Let's try that. A comma B equals 8, 7. Interestingly, all of these cycles seem pretty short. I wonder if they all are. I bet one of you could tell me in the comments. So there you go, there's your dive into Fibonacci number-based musical patterns. This was certainly more interesting than I was expecting, and I can definitely consider making a longer video about this in the future. And as always, if you want to try any of this for yourself, I've put links to the code in the description. Also, if you get a lot out of these videos and want to support my work on Scamp, consider becoming a patron. It really means a lot to me, and your membership also comes with bonuses like early ad-free access to videos, algorithmically generated scores and MIDI files, and perhaps the occasional experimental music application. Finally, if you haven't already, please like, subscribe, or roll yourself up in a giant blanket burrito.